we are going to learn how to optimize a different kind of problems. So suppose that we have a problem of in economy. Suppose that we have xt, the function with time, depending t is the time, t is the time. So xt, let's represent the capital, stock of capital, okay, and suppose that I or j, no, not j, let's call it f, capital F, okay, quantity that we call capital F, that depends on the time, on the stock, and the rate of production. Okay, let's call it, suppose that it is equal x prime t. So let's say x prime t is the rate of production. Suppose so this combination of these quantities form the function production at an instant at time t. So suppose at certain times of time, at t1 we have a quantity f t1 or t1, yes, t1 star x t1 t yes, t1 star and x prime t1 star, okay, and we continue like that. We can approximately along an interval, we estimate t1 and t2, we estimate the production, the profit of production, yes, or just the production, yes, or not the production, this rate of production, but this is the profit, okay, so a profit function, the profit, okay. So we have the, yes, profit at t, an instant. So suppose that like that over time from t0 to an instant t1, or from E to B, let's say, okay, we can have approximate values of these profit function p, so p at t2 star, etc., over interval t1 t2 t3, etc. Okay, then the total profit would be, so approximately p of t1 star delta, so t2 minus, so delta t1, let's call this interval of delta t1 over the time, and we continue like t2 star delta t2, etc. Okay, and suppose that n for n times 10 n instance like that, we approach the total profit like that, Tn. So if you look at this quantity, if we increase the number of times we are reading our profit, then we expect this is like, we call it Riemann sum, and usually the total sum is represented by e to b p of t dt, like that. So the total profit here, instead of writing it p of g of g, let's call it g, is the integral from, let's call it from t0 until the instant final tf, okay, initial and final instant of, so the function f t xt x prime t dt. Okay, so this is so a function of depending that on the function x. Okay, this is a function that depends on the function x, the stock, the capital of capital. Okay, so our interest now, the problem we are setting our interest. So how what stock, what capital or stock of capital will maximize, okay, what x t will maximize profit, maximize profit, the total profit, the total profit over 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 the interval of over the interval time t0 to f. Okay, that is, we are asking, so we are, which function, you see here, the instead of what we were used to study, we were considering point in Rn. This time we are looking for a function. So here our interest is to find the function x that we will choose it in a specific space. Here we will look for a solution that are C1 over the interval T0 Tf final. Okay, and we want to maximize what, the function g of x. Okay, so you see your x here is no more a point in Rn, but a function. So we are so it's a very new, it's different from the kind of optimization problem we use it to study and the one we established many theorems. Okay, so our purpose is to learn how to deal with, how we will be able to study such problems. First thing, as we did in, you remember, in Rn, we were interested in finding defining distance in our space that connects the points. Here also we have functions, but we can connect these functions. So with a distance, we measure how they are far. So this is the first specificity of the space C1 at from EB. Okay, so we define on C0 first, on continuous function, we define the distance and we name it, and we can use double bar, so of two functions x and y. Okay, the distance will be the maximum over t between a to b of the x, the values taken by the two functions, the difference. Okay, so this is how we measure. If we are working on C1, the set of C1 functions, we can use x minus y on C1 EB as the maximum of, we add for xt minus yt. Okay, so on C0, this is C0 plus the maximum of the derivative. But so this is just to give you an idea. We will not work with those norms. Okay, it's not, but just to connect things and to make analogies with what we are what we studied before. Okay, so this is important remark. So our purpose, we said in this section, is to study the problem. So to maximize, we want to maximize the integral from t initial to t final of a function depending on t, xt, and x prime t. We can have more complex sets, okay, c0 on t0 tf, but it's not only those conditions, so I would prefer keep it over a set of functions. Okay, let's say more, I'm looking for x belonging to u, okay, where u is included in C1 of T0 TF. Okay, and yes, so for a moment, this is our problem. This is our problem of interest. Okay, great. Now let's continue. So how we will solve the problem? Okay, so let's proceed slowly. So we want to establish necessary conditions. Where to look for candidates for optimality, necessary conditions. So we have different space, but we will use similar ideas. Okay, so suppose x star. So suppose x star, that is a function. Okay, is an optimal function, is a maximum solution, is a solution of the maximization problem, is a solution. Okay, let's t, we will use this function to move around the point x star. You will see how, but we will use it as t0 initial point, and the value at the final point is 0. Okay, it's always possible to find such functions, and we will construct a function xt moving from x star t plus a factor of mu of t. And you see why we are doing this. If you do the difference, okay, difference between the two will be an absolute value of alpha and mu of t. So if your mu function is well known, it's bounded, then we can control this distance by choosing an alpha very small, so that we are close. Okay, choose alpha so small, alpha small. Okay, so that x is close to x star. Okay, okay, great. Now and let's remark that x at t0 is equal, since mu at t0 is 0, it will be x star at t0, and y and x at t final, it also is x star at t final. So it takes the same and values at the endpoint. Okay, now let's consider the value of the function g at this new function we formed at x. Okay, so that is x star plus alpha mu. Okay, so this quantity, since this x star is noun, supposed noun, mu is fixed, so it will depend on just alpha. Alpha can vary, we can change it. So we will get the quantity depending on alpha. It's a function of alpha. So this is exactly t0 to t1, f at t1 at t, okay, t x star plus alpha mu plus and x, then the derivative x star prime at t plus alpha mu prime t dt. Okay, great. Now so it's a function of one variable, and now I at 0, we know it's g at x star, so it's the maximum value, so it will be greater than I alpha. Okay, for any alpha, let's say from small alphas in my alpha 0, then necessarily we have the derivative at 0 is 0. Okay, so let's express what is the derivative, and you will see the same idea we did for optimization problem in Rn. We are having the same kind of way to prove. Okay, so when to derive now, so this is another step. Okay, I think I will finish here. So let's continue. So the derivative here to compute, here we use many tools. We derive under the symbol integration. So it's f, so it will be df dt chain rule variable also, d alpha plus df with respect of the second variable dx d alpha, okay, with the component function, so x star plus alpha mu d alpha, then plus df du and the third variable of f, and then d of x star prime plus alpha mu prime d alpha dt, which gives us this one is 0, this quantity is 0, okay, and now then we obtain that t0 t1 df dx mu, okay, and here also mu prime plus df du and mu prime dt. Then we use a chain rule formula, okay. We have df du mu prime, we can write it as, so let's separate here t0 t1 one step and we are done, okay, mu plus, so this integral we can write it as df du mu applied to t0 t1 minus, okay, the integral from t0 t1 of the derivative. So I skipped the details here, but it's you can mu t dt. So the integration by part you can set is u df du, okay, then u prime will be d dt df du, which is this term, and the other one v prime, remember v prime will be mu prime, so v is mu, which is here, okay. And now we use the fact that mu is 0, so this quantity also is 0, okay. And finally we have something like that. Look at the last term we get. If we factor by mu, we will have df dx minus d dt df du, okay, and mu of t dt. And this is true for any mu that is C2 and equal to 0. And then there is a lemma. That gives us that necessarily this quantity inside the integrand fraction is 0, and which gives us the necessary conditions. Okay, so the main theorem, so I give here the main theorem. So the theorem for these kind of problems that gives us the necessary conditions. So if we have f c2 function, f c2, okay, in the variable t, x and u, okay, then the maximum if x star, if x star is such that what the maximum g of x star is the maximum of the function t0 t1 f of tx prime t dt over the set u, where u is the set of functions x that are in C2 from t0 t1 and that satisfy x t0 equal x0 x t1. So we are looking for solution like that, given initial and final conditions. And they are C1, not C2, they are C1. We need just second C1. Yes, they are C1, not necessarily C2. Okay, so we need just C1. Okay, so then if x2 is such that realize the maximum, then necessarily it is solution of df dx you derive your function applied at tx minus, okay, at t x prime minus the derivative of dt with respect of t of the derivative, partial derivative with respect of u of f. You apply it at t x prime, okay, equal 0. So this is how the first theorem what it says, and this is what we established. Okay, there is another theorem that tell us where is it global, if it is that it says if we have a candidate point and we have a convexity of f, then we can say that we have the maximum, we found the maximum. So here such that max or min respectively min, okay, so both either max or min, we have the Euler equations. These are Euler equations. They are the necessary conditions satisfied by an optimum point. So the second theorem we said without proving it, here it is. The second, so this is a necessary condition. This is the necessary condition. Here the sufficient conditions. Okay, so we need under the same assumption of regularity, if f of txu is concave respectively convex in the variables in xu, okay, and x and if and x star t satisfies the Euler equation, then x star, this x star solves the maximization problem, solves the maximization problem, respectively minimization problem. So this is also, so it is very helpful. So if it is so the candidates are solution of Euler equation. Now if we have concavity, for sure those candidates will be the solution. So this is exactly the ideas we developed in the other kind of problems. So let's skip the proof and just try to see an example of application. Okay, so let's do one example quickly. An example. Okay, so suppose that you are asked to solve maximum the integral from 0 to 2 4 minus 3x2 minus 16x prime minus 4x prime square, okay, a minus t dt. With x0 for such that x0 also is minus 8 over 3 and x at 2 is 1 over 3. Okay, so we will set, so let's bring ourselves with the notation, previous notation. So our function txu, I will set it as 4 minus 3x2 minus, so the role used by u, substituted by u is x prime, so minus 16u minus 4u square, everything multiplied by e minus t. Great. Then so it is clear that f is c2 even in R3 in the three variables, there is no problem. And here my g of x is the integral from 0 to 2 of f tx u dt, as sorry, not u, so xt x prime t, okay, dt. So this is we are in the same category of problems, and many problems are classified in optimization, so we need to work exactly in the same under the same assumptions. Okay, now we are which solution, where we look for our solution, we will look for them in the set of functions that are c1 over the interval 0, 2, and take the endpoint values minus 8 over 3 and x2 equal 1 over 3. So I will look for my solution. So I'm exactly in the same condition. So a candidate, look for the candidate. So a candidate is solution x star x, okay, is solution of Euler equation. Okay, Euler equation. So what is, let's write Euler equation. Euler equation here, we know that it is, we established Euler equations. They were that, yes, dfd. So it's df dx minus ddt df du applied at t x prime dt, okay, equals 0. So I need to express what is df du. So let's do our calculation here. So I need to express fx. So I need fx here. So maybe I will write it above. So we need to save time, space here. Okay, so fx, I see it, is equal to minus 6 if I look to my definition of the function of txu. So minus 6x and a minus t times fu, the derivative u in u, I will have minus 16 and minus 8u and a minus t. Great. Now fu, I need it applied at tx and x prime, so it will be, I get it's better to write things like that so that you don't mix the variables, etc. Now I need to derive dt of fu at tx x prime. You see, when you do it like that, it's much better. So here you see that you have to derive a product of two functions. So it will be minus 8x second times a minus t. Then you keep this plus minus 16 minus 8x prime and minus a minus t. So if you take minus a minus t in as factor, so you will get minus 8 x second. We will have plus 8 x prime and minus plus 16 a minus t. So here is my quantity. Now Euler equation becomes Euler equations. We can write it, so fx is minus 16x a minus t. Okay, then I need the minus the derivative, this derivative, so it's minus 8x second minus 8x prime plus 16 et minus t, I mean. So here, yes, we can see it well, equals 0. So simplifying by e minus t, we get the equation x second minus x prime minus 3 over 4x equal 2. This is a linear equation, differential equation of order 2. So there is a method how we solve it. We assign the characteristic equation, second degree equation, 4 over 4 equals 0. We have two roots, so r1 equal minus 1 over 2 and r2 equal 3 over 2. And knowing the solutions, we deduce a general solution of this equation. So the general equation will be plus, yes, general equation will be then a exponential minus 1 over 2t plus b a constant ba to 3 over 2t plus particular solution which is minus 8 over 3. Okay, so it gives us the particular solution, this one. And to identify, to get x star, we use the initial and the fact that x0, okay, a and b are deduced then. Okay, so to find a and b, use, okay, the fact that x0 equal minus 8/3, so it will give us a plus b minus 8/3, and x at 2 is 1/3, which is a minus 1 plus b a3 minus 8/3. Okay, so we deduce the two, we deduce a and b, and like that we have our solution. Okay, so we will get then the formula for xt, but this is just a candidate. To check that it is a solution, we need to check the convexity, the concavity of f in xu. Okay, so concavity, so let's check here, concavity of f, in xu. So I need to, for example, use the Hessian, look for the Hessian of f. Yes, I have the partial derivative, so f, the Hessian of f, so it's given by f xx, f xu, f ux, and f uu. So fxx, so I have fx here, so I will get minus 6 a minus t, doesn't depend on u, so 0 0, and u, in u I will have minus 8 minus 8 a minus t, you see, and you see that we have here d1 equal minus 6 a minus t. Okay, d2 is multiplying, so the determinant will get a 48 a minus 2t. So minus 1 d1 is positive, and minus 1 2 d2 is positive, so it is f is concave in xu, and x star is solves the problem, solves the maximization problem, max problem. Okay, so it worked. So this is how yes, we deal. We don't have many theorem for a moment, but you have already answers, identify the candidate, and check concavity or convexity to confirm whether or not it is a solution.